Welcome, gentlemen, to Unit 2, Lesson 1. By the end of this lesson, I hope you'll be able to say that you can connect algebraic and graphic representations of transformed polynomial functions and identify even and odd polynomial functions from algebraic and graphical representations. That was a lot. Well, the second half of that I already know you can do because we covered that last unit, and we covered that for all cases. So that shouldn't be a problem for you. So we're not going to spend any time on that. If you have any questions about that, you can look back at the last video that we made and look at your homework from that. Alright? So why don't you take a minute and pause this and write this down, and we'll get started. Alright, so here's our think about it question. Hypothesize how will the function f of x equals x minus 8 cubed plus 6 was transformed from its parent function x cubed. Alright, why? Well, that why question is kind of silly, so you can think about it. Why would anybody transform a function like that? Well, think about it, come up with some sort of solution and write it down. Alright, and what do you think the transformation is? I want you to write down what you think the transformation is here. Alright, and then we're going to come back to it at the end of the lesson here. And hopefully you'll be able to finish it off and have a better idea of what's going on, okay? So pause this, write it down, think about it, then write about it in your notes, and then at the end of the lesson we'll come back and answer it completely. Alright, we keep talking about parent functions, alright? And in particular on this unit we're going to talk about parent functions for polynomials, but I kind of have a feeling you're not sure what a parent function is. So a parent function is the most basic simple function without any transformations or any changes, alright? So we've already talked about quadratics, and the parent function for a quadratic is f of x equals x squared. So there's a function, there's x squared, and it's not changed. That's just our basic simple parabola, alright? That's a quadratic one. Then, you kind of go up a notch, right? The next one, if that's squared, then the next one's going to be f of x equals x cubed, right? That's going to be the parent function. And f of x equals x to the fourth. And we keep doing this on and on and on for all polynomial functions. F of x equals x to the n power, okay? So we can do this forever and ever and list out parent functions. So there's no transformations here in our functions at all, okay? So those are the parent functions for polynomials, and they're important, because we're going to basically transform these functions, all right? They all go through the origin, okay? Just so you know, each one of these functions goes through the origin. That's something you may want to know, right? Because the x squared, that has a vertex of 0, 0, right? There's no transformation in that one, okay? So let's take a look at the next slide. Are you ready? Boom. Okay. Based on what we know about vertex form of a quadratic function, are there things we can conclude about about transforming polynomial functions? And can we generalize this for all functions? That's the question you should be asking yourself. So, what was vertex form and what did it tell us? You need to remember that, right? So vertex form was f of x equals a times x minus h squared plus k. Okay? So what did we get here? Well, what information did we get out of this? Well, what did a tell us? What did a tell us? A told us, right, if a is not negative, so a is greater than 0, right, then my quadratic opens up, right? That means there's no reflection across the x-axis, right? So that means no reflection. across the x-axis. And then if a was negative, what did we know? That means a is less than 0. That means it reflects across the x-axis. Right? That was a big deal, wasn't it? A also tells us something else, right? If a is greater than 1, right, that meant we had a vertical stretch by a factor of absolute value of a. So if a was a fraction, which means it's between 0 and 1, right? That means I had a vertical see, this is a stretch, then that's going to be a compression. By absolute value of a. And this is also, this is a absolute value of a and absolute value of a. Let's just be clear on that. Alright guys? So that was all from one little letter. We get all those transformations, right? That was just from A. What do we get from H and K? Do you remember? Right, H and K is the vertex, and those were our transformations. So H is a shift left or right, right? Left or right. And K is a shift up or down. Well, does this have any relationship at all to perhaps maybe the other functions, right? So this is quadratic, right? So its parent function was f of x equals x squared. Can I write something in a similar form to the vertex form for a cubic or a quartic or a polynomial of degree 5, or a fifth degree polynomial, right? That has one term. That means probably not much to most of you, but when I come back I'll explain it to you. Okay? Does that make any sense? Can we take this and generalize it to those other parent functions? All right, I want you to try that and generalize it to those other functions. The answer is yes, we can. Okay, we can generalize it. So, for example, if I had a cubic, my function, if I were to have the transformations, I would have f of x equals a times x minus h cubed plus k. Barely fit that in there, right? So it looks exactly like our vertex form, but it's not. It's not vertex form because there is no vertex for a cubic, right? But it does give us our transformations. A still does the same things, and H and K still transform my function. They're just not called the vertex now. They are my shift left or right or up or down, and A still reflects it across the x-axis, or tells me whether I'm compressed or shrunk, right? And the parent function for this would be f of x equals x cubed, all right? So you can generalize this to all functions, and you can generalize this to any polynomial function, okay? So I would like you to try in your notes to write down how you might generalize this for all functions. If you don't know how to do it, you can look it up, and if not, that's okay. I still want you to try. I want you to look it up. yeah, just look it up if you don't know, okay? But it can be generalized for all functions, and that is really awesome. We can write down what our transformations are for all functions, so you don't need to specialize in just like, okay, so this is how I transform absolute value function, and this is how I transform signed function. It's going to be the same no matter what it is, no matter what the function is. These transformations are going to go across all things, and that's what makes it so amazing. So I'd like you to generalize it for all polynomial functions. And really, when you do that, you're generalizing it for all functions all together, which is amazing. All right? Now I'd like you to take a minute and try these problems, all right? Numbers 20 through 25, I want you to write what the transformation is. Notice there's a minus x here. Where is it? Here it is. Dun, dun, dun. Hold on. Let's highlight that. That minus x right there, right? You see it? Right there. There's that minus x, all right? That actually transforms my function. I'd like to see if you guys can figure out how that will transform my function, all right? The shifts are all the same. Have fun with this. I mean, you need to figure out if they can be written, right? And tell me what the transformation is, if you can. Well, you can. You write the transformation for all these, all right, guys? And then I want you to do number 26 and 29. They're great problems. And enjoy, gentlemen. Enjoy.